Lighthouse Scientific Education presents a lecture in the Measurement and Numbers series. The topic of the lecture, Math for Chemistry, Part 2. Material in this lecture relies on understanding of the previous lecture, Math for Chemistry, Part 1. Math for Chemistry. Since this is a two-part lecture, which builds on the first part, we will briefly review those principles that helped us devise a strategy for solving for a variable. We started with the fundamental properties. We made repeated use of the identity laws of addition and multiplication. We practiced solving for a variable. In this lecture, we will also address the topic of solving for a variable. This time we will focus on solving multivariable equations. Then we will tackle percent. Percent also provides us with an opportunity to discuss a problem-solving technique used in these lectures. Since the identity laws were so helpful in the previous lecture and will be used repeatedly in this lecture, we will review them along with processes for generating zeros and ones to solve an algebra problem. The identity laws of addition says a plus 0 equals a. Adding 0 to a value returns the value. The law holds when 0 is subtracted, a minus 0. It also equals a. The identity law of multiplication says a times 1 equals a. Multiplying a value by 1 returns the value. The law also holds when a value is divided by 1. A divided by 1 equals a. The addition and multiplication identity law, along with the process for generating zeros and ones, combines to form the basis for general algebra. Consider the problem 5x plus 7 equals 2x minus 2. The first step in solving this problem is to collect like terms. That is, bring all the x's to one side of the equation and all the numbers to the other side. The problem is solved when one side of the equation has x by itself and the other side has the numerical value. Note, it's far easier to use the addition identity law before the multiplication identity law. The multiplication identity law should be used as the last step. Our first mathematical maneuver will be to turn 5x plus 7 into 5x plus 0. In other words, to make the 7 a 0 so that we can use the addition identity law. This is done by subtracting 7 from both sides. The associative law of addition allows us to group the 7s, and solving the math inside the parentheses gives us a 0, and 5x plus 0 equals 5x. Now we need to move the 2x over to the left-hand side of the equation. We do that by subtracting 2x from both sides. Grouping shows us that subtracting 2x from the right-hand side of the equation will give us a 0. And 0 minus 9 is negative 9. The right hand of the side is simplified to 3x. Now we're ready for the multiplication identity law. We need to turn that 3 into a 1. We can divide both sides by 3. 3 divided by 3 is equal to 1. And 1 times x is equal to x. Negative 9 divided by 3 is a negative 3. And so we have our solution, x equals negative 3. The identity law and the creative use of 1 and 0 are the basis for algebra. Problems, however, sometimes are more complex. In chemistry, the algebra often involves equations with more than one variable, or multiple variables. For example, the gas law. It relates pressure and volume to temperature. PV equals nRT. And then there's the concentration dilution equation. It has C1 times V1 equals C2 times V2. And the density equation. The density is mass over volume. D equals M over V. Now, this isn't time to investigate how and why these equations work. That comes later. These are just examples of multiple variable equations. Before we move on, let's be clear what the term variable means, since it will come up often. Variables are properties or values that can change under different circumstances. As such, they are often represented by a letter. Temperature, T, is often a variable because it changes. At any one time and place, temperature is constant. But if you do not measure it at that condition, it is an unknown. Volume and pressure, V and P, are variables, even when we know their values, because they can change under different circumstances. Chemistry homework often has problems that you solve by isolating a particular variable and plugging in numbers for the other variables. For example, a problem might ask you to solve for pressure, P, in the gas equation, or for the dilution concentration, C2, or maybe volume, V, in the density equation. Perhaps you've noticed that these equations are all multiplication and division, and no addition and subtraction. That will be more common than not. We can solve these type of equations using the same set of processes we used with the previous algebra problems. And since we're dealing with multiplication, we will use a lot of the identity law of multiplication. When we get to the study of solutions, we will see this before and after dilution equation. Perhaps we'll come across a problem that wants us to solve for the diluted concentration C2. It will be the practice of this lecture to solve the equations algebraically before entering the values into the problem. What does solve the equation algebraically really mean? In short, it is the practice of leaving the variables in the equation and isolating through algebra, alone on one side of the equation, the one variable of interest. After the isolation has occurred, the student then enters the numbers from the problem into the new equation and solves math on their calculator. Putting the numbers in before isolating the variable may seem easier and faster, but it just leads to more math errors. Okay, let's go after that equation. We want C2 alone. And it doesn't matter which side of the equation it's alone on. We can use the identity law of multiplication if we can turn V2 into a 1. C2 times 1 is C2. And that is accomplished by dividing both sides of the equation by V2. Remember, whatever you do to one side of the equation, you have to do to the other. As we've seen before, anything divided by itself is equal to 1. So, C2 times 1 is C2. Therefore, C1 times V1 divided by V2 is equal to C2. The real homework problem will include numerical values for each of the variables on the left-hand side of the equation. Another example of a homework problem could involve the gas law. Say you're provided with numerical values for each of the variables in this equation except for T. That's temperature. Your job is to isolate the temperature variable. Examining the equation, we see that it is all multiplication, which means that we can use the identity law of multiplication. If we can turn n times r into 1. Up until now, we've only been turning one value at a time into a 1. But that doesn't mean we're limited to just one variable. For instance, we could turn a, b, c, d, e, f, g into 1 if we divided it by a, b, c, d, e, f, g. Anything divided by itself is 1. So how can we turn n times r into 1? Yes. We divide both sides by n times r. Grouping shows us that n times r divided by n times r is equal to 1. And 1 times t equals t. T equals PV over n times r. This is the point where the values of the known variables are added in, units are canceled out, and the math is done to yield the solution. One note, when doing this problem, if the units on the left-hand side of the equation do not cancel out to just temperature units, then there is probably an algebra error. Paying attention to units is a great way to catch mistakes. This last example is the type that students have the most trouble with. We will solve the equation algebraically two ways. The first, we will use the same kind of steps we employed in the previous two problems. The second, we will use a common algebra trick. In the lecture on density, a third way will also be introduced. This problem, we will use density equation, D equals m over v. We will say that we have numerical values for D, density, and m, mass, and we're asked to solve for v, volume. We're going to isolate v on one side of the equation and not in the denominator. Up until now, the variables being isolated have always been in the numerator. This one is in the denominator, and that is why it causes students so much trouble. Let's get v into the numerator. How do we do that? Well, not surprisingly, we can use the multiplication identity law if we revisit our notion of 1. We know that dividing a value by itself will get a 1. That's because both numerator and denominator have the same value. Well, in this instance, the v is already in the denominator. So what we need is to put the v into the numerator. We can multiply both sides of the equation by v. We get v over v, which becomes 1, and v in the numerator on the other side of the equation. M times 1 equals m. This multiplication step is the one that befuddles many students. It looks like an extra step that doesn't appear to help isolate v. But v is no longer in the denominator, and that is a step forward. We now have an equation with v in the numerator, which is a much more comfortable position. To isolate v, we need to turn the d into a 1. D over d is 1, and v times 1 is v. V equals m divided by d. This is a basic level of algebra needed for chemistry. We can also tackle this problem in perhaps a less convoluted manner. Any term or value can be made into a fraction by dividing it by 1. It's not a necessary step, but it helps demonstrate the process. We can get the v into the numerator by cross multiplying, and cross means across the equal sign. That is the numerator of the first fraction, d, times the denominator of the second fraction, v, equals the denominator of the first fraction times the numerator of the second fraction, which is m. V times d equals 1 times m. And 1 times m is m. Now we have to take care of the d. Turn the d into a 1 by dividing both sides by d. D over d is 1, and v times 1 is v. V equals m divided by d. Understanding this level of algebra is probably the single biggest advantage a student can bring to the study of science. When we struggle with the math, while we're struggling with new ideas, it makes learning more frustrating and more difficult. On to percent and problem solving. A ratio, or a fraction, taken 100 times is a percent. Percent means per 100. In mathematical terms, it is a fraction, a numerator over denominator, times 100. Written in this form, we see the relationship between the values that make up the ratio and its representation as percent. The percent is simply a larger version of the ratio. In the ratio, the denominator represents the size of a whole, or how many parts make a whole. The numerator represents the portions or parts of the whole. Incorporating that language, numerator as the part and denominator as the whole, we have a more useful expression. Part divided by whole times 100 equals percent. There is another version of this equation that can sometimes be more useful in solving percent problems. It is derived by dividing both sides of the equation by 100. And as we know, divide 100 by 100, we have 1. The new expression is an equality of two fractions. This form is set up to do cross multiplying. Both ways of writing the percent equations have their strength, and both are useful. As stated, the percent is based on a fraction or ratio. Consider this hypothetical pie. It is cut into 3 pieces. The whole of the pie is 3 pieces. The part, colored blue, is 1 piece. Putting these values into the percent equation, part over whole times 100 equals percent, we have 1 over 3 times 100 is equal to 33%. A third of the pie is equal to 33.3% of the pie. Sometimes the percent is known and the ratio needs to be found. Take this pie. 83.33% of the pie is blue. What's the ratio? Here we use the other representation of the percent equation. Plugging in 83.33 into percent, producing an equation that needs only division to be complete. And that is 0.833. That is the decimal form of the ratio. Decimal is an acceptable way of writing the ratio. Looking at the pie, we can see that 5/6 of the pie is blue. It should not be surprising that punching the ratio 5/6 into your calculator will get you 0.833. Typical percent problems involve solving for one unknown variable. The percent equation has 3 variables: the part, the whole, and the percent. Most percent problems will give you values for 2 of the variables and ask you to solve for the third. We can use our practice with the percent problem to develop our general problem-solving skills. For problems, the solution is found by 1. Identifying the known and unknown variables. That involves reading and understanding the problem, as well as writing the variables and the values for the variables down on paper. Secondly, find and solve the equation algebraically. That is, find an equation that relates the known and unknown variables, and then isolate the unknown variable through algebra. And finally, input the known values and solve. Here's where the numerical values written down in step 1 are used. Percent problems are word problems, and word problems present their own difficulties. The steps outlined for solving percent problems are the base of a broader approach that breaks word problems down into smaller, easier pieces. This approach is one that is adapted in these lectures. It is not the only approach, but it is rational and it is reasonable. Let's look at it more in detail. First step, identify the known and unknown variables. This information is put under the heading Setup. Here the essence of the problem is reduced to a series of variables and numeric values. These known and unknowns are pulled out of the word problem and written down on paper. The problem is not solved here. This step is collecting the information necessary to solve the problem. It is a thinking part of the solution. Setting the problem up is separate from actually calculating a solution. So we're breaking the larger problem down into smaller problems. That's a very, very useful technique. For demonstration purposes, we will pretend that we are tackling a percent problem, the part as the unknown. The second step is to find and solve the appropriate equation algebraically. This step is under the title Relationship. The relationship is the equation or equations that relate the known and unknown variables in the setup. The setup has taken us out of the word problem and listed the components of the solution. Somewhere there is an equation that has the unknown variables in terms of the known variables. The percent equation is the relationship in our demo problem. It is not, however, solved for the unknown. Part is not isolated. The second part of a relationship, after the find, is to algebraically solve the equation for the unknown, like this. Notice that we did not stick numbers into the equation before we isolated the unknown variable. That is solving algebraically. The third step is the satisfying one. Input the values and solve. Take the values from the setup, put them into the solved equation from the relationship. Now we get our calculator and we finish the job. Here's some general advice. Don't use your calculator to think. All it can do is math. Think first, math last. Analysis. Difficult problems can be made simpler by breaking them down into smaller tasks and focusing on just the task at hand. Okay. On to some percent problems. Here's a typical problem using chemistry language. Don't worry if there are elements of the problem that you're not familiar with. We're only interested in using our problem-solving skills on a percent problem. Your lab experiment recovered 7.3 grams from a starting amount of 10.0 grams. What percent was recovered? We will use the 3 steps to consider the problem and solve the problem. First, identify the known and unknown variables. Remember, there are only 3 in a percent problem. Percent problems will give you values for 2. Write out the variables on a piece of paper. Search the word problem to find out which ones you know and which ones you don't know. This is not the place for an equation. We are not ready for an equation. Let's take our time and build a solution. Now, looking at the problem, we can see that the starting material is the whole, and it is 10 grams. Write that out. Only part of the starting material was recovered, so 7.3 grams must be the part. Write that out. And percent. It's an unknown. We can put a question mark there, or maybe an X as an unknown variable. That's a good approach too. We're going to stay with the question mark. Now that step 1 is done, we'll move the known and unknown variables to the side, and we'll go to the second step, and we'll find the appropriate equation when relating the known and unknown variables, and solve that equation algebraically. That means to isolate the unknown variable. In this case, that is percent. To find an equation, we consider the variables in the setup. We ask, what equation relates the known and unknown variables? What relates whole, part, and percent? The percent equation. We can make our work easier if we choose the one already solved for percent. Now we can move on to the third step. input known values, and solve. The part, 7.3 grams. The whole, 10.0 grams. Multiply by 100 gives 73%. The lab had a 73% recovery. The next problem is also a typical chemistry problem. Again, we are only interested in the percent element of this problem. 65% of a material is oxygen. How much oxygen is there in 1.3 grams of the material? The first step, identify the known and unknown variables and write them down. Looking at the problem, we see that all of the material, the whole, is 1.3 grams. The other known variable is percent. It is 65. What we don't know is what part oxygen is of the whole. Our setup is complete. Next, we need to find the appropriate equation and then solve that equation algebraically. We need an equation that relates part, whole, and percent. We want to isolate part in that equation. Either of the percent equation will work. This one might be a bit easier. It is the relationship equation, but it is not solved for part. And there are several ways of isolating part. Since the equation relates to fractions, cross-multiplying is a reasonable step. 100 times part equals percent times whole. And we can use the identity law of multiplication. How can 100 be turned into a 1? Divide both sides by 100. Grouping shows that 100 divided by 100 is 1, and 1 times part is part. We have the isolated form of our relationship. The final step is to input known variables. The whole is 1.3 grams. The percent is 65. Taking out our calculator and properly inputting the values gives us a part of 0.845 grams. So 65% of 1.3 grams is 0.845 grams. Our last example is a reverse of this previous problem. The numbers are the same, but the unknown has changed. Again, we are interested only in the percent part of the problem. You know that a material is 65% oxygen. Your experiment finds 0.845 grams of oxygen. How much of the material did you start with? Step 1. Identify the known and unknown variables. Looking at the problem, we see that oxygen is a part of the material. So part is 0.845 grams. The percent that oxygen makes up is 65. The whole is unknown. The setup is complete. Next, we need to find the appropriate equation and then solve the equation algebraically for whole. Either one of our percent equations will work since they relate to three variables. This one worked pretty good last time. Cross-multiplying is a good start. Whole can be isolated if percent is made into a 1, and that's done by dividing both sides of the equation by percent. Grouping shows us that percent divided by percent is 1, and 1 times whole is whole. The final step is to input known values and then solve. The part is 0.845 grams. Percent is 65. Taking out our calculator and doing the math gets us 1.3 grams per whole, just like it was in the previous problem. We have seen here that problem-solving practice of setup, relationship, and solve works regardless of which term is the unknown. Let's recap what we've covered in this lecture. Chemical equations often have multiple variables. Homework problems often involve isolating a particular variable. Identity properties of addition, a plus 0 equals a, and multiplication, a times 1 equal a, are used to isolate variables. Percent means 100. A ratio taken 100 times is a percent. There are two useful forms of the percent equation. One shows the relationship between the ratio and the percent, and the other is useful when isolating for part or whole. Solutions to percent problems and, as we will see, other word problems are found by identifying the known and unknown variables. These are put into the setup. Find and solve the equation algebraically, that is, find an equation that relates the known and unknown variables in the setup. And finally, input known values from the setup into the relationship and solve. And that concludes the lecture on Math for Chemistry Part 2. Math and chemistry require practice. It's not enough to follow a lecture. To build understanding requires effort and diligence.